We will now turn our discussion to confidence and prediction intervals for the regression line. So let's recall that the variance of our estimator for the intercept B0 is C sub 0, 0 sigma squared. Our variance for the estimator for the slope is C sub 1, 1 sigma squared. And the covariance for those two estimators we computed in a homework problem is C sub 0, 1 sigma squared. We will use those facts to derive our confidence and prediction intervals. So what we're going to do first is look at a linear function of our two parameters beta 0 and beta 1. So we're going to let theta be a0 beta 0 plus a1 beta 1. And then the estimator theta hat would be a0 beta 0 hat plus a1 beta 1 hat. Then the expected value of theta hat is going to be the expected value of a0 beta 0 hat plus a1 beta 1 hat. The linearity of expectation makes that a0 expectation of beta 0 hat plus a1 expectation of beta 1 hat. And then beta 0 hat and beta 1 hat are unbiased, so that just becomes a0 beta 0 plus a1 beta 1, which is of course theta. So theta hat is unbiased. But let's also look at the variance. The variance of theta hat is going to be the variance of a0 beta 0 hat plus a1 beta 1 hat. And note that beta 0 hat and beta 1 hat are not independent. In fact, we saw that beta 0 hat was actually a function of beta 1 hat. So when we compute that variance, we need to use a fact back from probability that that variance is going to be a0 variance of beta 0 hat. That's an a0 squared. Plus a1 squared variance of beta 1 hat. Plus 2a0 a1, the covariance of beta 0 hat and beta 1 hat. Okay, now you can see how we're going to use those facts above. This becomes a0 squared c sub 0, 0 sigma squared plus a1 squared c sub 1, 1 sigma squared plus 2a0 a1 c sub 0, 1 sigma squared. And now I'm going to rewrite those, noticing that two terms are in all three of those terms that I have there. So each one of these terms contains a sigma squared, and each one contains s sub xx. So I'm actually going to factor those out. Then what's left over is an a0 squared over n, sum from I equals 1 to n, x sub I squared, when I replace c sub 0, 0. And then an a sub 1 squared, when I replace c sub 1, 1. And then minus 2a sub 0, a sub 1, x bar when I replace c sub 0, 1. So that gives us a form for the variance of theta hat. Now I want to move on to a special case of a linear function of theta hat, of beta 0 and beta 1, which is theta hat. So we're going to let y star be the predicted value for x star. So we're just going to give this a new name. Instead of y hat, we're going to say that y star is the point on the regression line given by beta 0 plus beta 1 x star. What we should notice is that y star is a linear function of beta 0 and beta 1. But in this case, the a0 is 1 and the a1 is x star. Well, then y star hat as an estimator is unbiased because the expected value of y star hat is just going to be beta 0 plus beta 1 x star, as we showed above. Now, what is the variance of y star? Well, the variance of y star is going to be plugging in a0 equals 1. We're going to get 1 over n, the sum from I equals 1 to n of x sub I squared. And then I'm going to plug in a sub 1 so that the next term becomes x star squared. And then I'm going to plug in a sub 0 equals 1 and a sub 1 equals x star to get minus 2 x star x bar. And this is all going to be multiplied by sigma squared over s sub xx. Now it turns out that I can rewrite this as 1 over n plus x star minus x bar over s sub xx times sigma squared. So why is that the case? Well, I'm going to show you how to manipulate 1 over n s sub xx times x star minus x bar squared. So essentially, I'm going to show you how to manipulate this term if I multiplied it by s sub xx. Okay, so that's 1 over n, and then we have to substitute in our definition of s sub xx. S sub xx is x sub I minus x bar squared, and then I'll get plus, and then I'm going to square that term. So I'm going to get x star squared minus 2x star x bar plus x bar squared. Okay. In the next step, I am going to square the term that's in the sum. So it's 1 over n, sum from I equals 1 to n, of x sub I squared minus 2x sub I x bar plus x bar squared. And then the rest of the terms remain the same, plus x star squared minus 2x star x bar plus x bar squared. Okay, let's see. So this first term is one that I want to stay in, the sum from I equals 1 to n x sub I squared times 1 over n. That is a term that I want to appear. The next term I'm going to write as minus 2 over n x bar, the sum from I equals 1 to n x sub I. And then the last term I'm going to write as the sum 1 over n sum from I equals 1 to n of x bar. And then I still have my three terms at the end here, plus x star squared minus 2x star x bar plus x bar squared. Okay. If we look at this term right here, and we add the 1 over n, that term is in fact x bar. It's 1 over n, the sum from I equals 1 to n of x sub I. So that's x bar. And if we sum x bar n times, then this term right here is also just x bar. And so what we have is that we have a minus x bar here. We have a minus 2x bar here, a plus x bar here, and a plus x bar here. And those three cancel. So what we're left with is 1 over n, sum from I equals 1 to n, x sub I squared, plus x star squared minus 2x star x bar, which is exactly what we wanted right here. Okay, so now we have the variance of y star, and that will help us come up with the confidence interval for the expected value of y star. So the confidence interval we're going to write as beta 0 plus beta 1 x star, like we've written before, plus or minus, and now we want the t statistic, t sub alpha over 2, and then we're going to multiply by the standard deviation of y star, or the standard error, and that is going to be s times the square root of 1 over n plus x star minus x bar squared over s sub x x. And the degrees of freedom for this problem is going to be n minus 2. So let's make sure we understand that this term right here, that's the standard deviation for y star. You can see that by looking at the variance for y star, which is right here. And what I've done is I've replaced sigma squared with s squared, and I've taken a square root. So when I replace sigma squared with s squared, that's why I need to use the t distribution. Okay, so now we have a confidence interval for the expected value of y star. So let's look at an example to compute that confidence interval. So previously we found that the regression line for 5 data points, as shown below, was y hat equals 1.5 minus 0.6x. And what we would like to do is find a 90% confidence interval for the expected value of y when x star is -2, 0, and 2. And then we want to plot that confidence interval on the plot below. So what I'm going to do is I'm going to first use this table to fill out some points and things that we're going to need. So what we want to do is we want to find y sub I hat. Those are going to be the estimates of y sub I using our regression line. So the first one I'm going to fill in is when x sub I is 0, clearly it's 1.5 minus 0.6 times 0. So my intercept is 1.5 for the line. You can actually see it right there. Okay, so the slope is negative 0.6. So I can easily see if I subtract 0.6 that the next point should be 0.9 and the next one should be 0.3. And then if I want to go the opposite direction, I can add 0.6 so that this point is 2.1 and this one is 2.7. And that gives us the points on our regression line. Okay, now I want to find the residuals because I'm going to need those for this computation. So the residuals are y sub I minus y bar. So 3 minus 2.7 is 0.3. The next residual, 2 minus 2.1, is negative 0.1. The next residual, 1 minus 1.5, is negative 0.5. 1 minus 0.9 is 0.1. And 0.5 minus 0.3 is 0.2. Okay, so I'm going to use those residuals to help me compute the sum of the squares of the error. So the sum of the squares of the error is the sum from I equals 1 to n of y sub I minus y hat squared. And so that's going to be 0.3 squared plus negative 0.1 squared plus negative 0.5 squared plus 0.1 squared plus 0.2 squared. And if we sum all that up, we're actually going to get 0.4. So we computed the sum of the squares of the error because our sample variance s squared we saw before is the sum of the squares of the error over n minus 2. That's going to be 0.4 over 5 minus 2. That is 0.1333. We're going to need to know s, so s is the square root of 0.1333. Okay, now using this data, because we did this as a previous example, let's recall a couple things. First of all, x bar, the average of the x's, was 0. And we also computed s sub xx, that was 10. So that's some information that we need. We also need that since the degrees of freedom for this problem is 3, okay, we're going to be doing t sub alpha over 2 or t sub 0.05 because we're doing a 90% confidence interval. And so we're going to need that t value. I'm going to go back to the t chart. The t chart, 4.05 with degrees of freedom 3 is going to be 2.353. So I'll zoom in there so you can see it. So now we're going to go back. So this is going to be 2.353. And now I have everything that I need to compute the confidence interval. So the 90% confidence interval is going to be my line 1.5 minus 0.6 x star plus or minus the t statistic or t value, t.353 times s, square root of 0.1333, times the square root of 1 over n, that's 1/5, plus x star minus x bar, which is 0, squared over 10. So that's going to be our 90% confidence interval. And what I would like to do is just compute that for a few values. So we're going to compute that for x equals minus 2, x equals 0, and x equals 2. So all I have to do is plug in x equals minus 2, 0, and 2 to this formula. So I'm going to save myself a little bit of writing here. I'm going to copy this formula 3 times. And then I'm going to plug in what x star is. So in this case, x star is -2. And when I run this formula, I get an interval, because I'm both adding and subtracting, an interval of 2.03 to 3.37. And I encourage you to do that on your own. Okay, so now I'm going to plug in an x star of 0. And when I do that, I'm going to get an interval of 1.12 to 1.88. And then I'm going to plug in 2 for this interval. And when I do that, I'm going to get an interval of -0.37 and 0.97. Okay, so these were my confidence intervals for -2, 0, and 2. Okay, I'm going to put these on my chart here so that I can use them. So for -2, it went from 2.03 to 3.37. For 0, it went from 1.12 to 1.88. And for 2, it went from -0.37 to 0.97. Okay, so now I want to plot those on this plot. Okay, so first I'm going to start with for -2. So at -2, I want to go from just about 2 to 3.37, so a little bit above 3 there. Then for 0, I want to go from 1.1, so maybe about there, to 1.88, so maybe about there. And then finally, for 2, I want to go from -0.37, so maybe about there, and then up to 0.97, so about there. And if I was to fill in some more points, my interval would kind of look like this. And I want you to see that this interval is actually narrower here than it is at the ends. So it's narrower at the middle than it is at the ends. And that's actually a feature of these confidence intervals around the regression line. I also want you to notice that this confidence interval for the mean does not necessarily include all of the data points. Notice that this data point's not in the confidence interval. And that's because this is not a confidence interval for the data, it's a confidence interval for the mean or for the regression line. Okay, so it's not supposed to necessarily include all the data points. It is supposed to be a 90% confidence interval for the line, the regression line.